Welcome back, dear students. Today we are looking at the von Neumann architecture. Von Neumann architecture. This is a computer architecture that provides a single shared memory for data and instruction. It is also known as the von Neumann model or the Princeton architecture. So, the von Neumann architecture is mainly characterized, the main characteristic of the von Neumann architecture is that it uses a single shared memory both for data and for instruction. This architecture uses the idea of storing program instruction and data in main memory and moving them between memory and the processor. Von Neumann architecture is used in many modern computer systems. It consists of 1. A processor, 2. Connections for input and output devices, 3. A memory unit that can communicate directly with the processor, and lastly, secondary storage for saving and backing up data. As you can see, this is the von Neumann architecture model. This is the processor, and we said that the processor contains three units, like the control unit, the arithmetic logic unit, and registers. And we said we have five different types of registers, as you can see. These registers are going to be mainly or better explained, where each of them will be given its purpose, where we shall be treating the components of the processing unit. So now, as we were saying, we have the control unit, the arithmetic unit, and the register, each working together as the processor. Now, we have the input-output controller, from which the input and the output devices send and receive data respectively. That is, the input devices with the use of input controller are able to send in data to the processor for processing, and after it is done, the same input output controller provides the information to the output devices, and also the I/O controller exchange data and information with the secondary storage unit in such a way that if there is data that was backed up and needs to be output, it is sent to the output devices and vice. And also, after a particular execution is done, we use this same line to save the result. Now, you will realize that we have only one memory known as the data instruction memory, which is used by the processor with the use of these three lines. And these three lines are the different buses that we have in a computer, still to be explained under the components of the processing unit. Now, what I want you guys to pay attention is that at this level, the output devices just receive information, whereas the input devices send in the information. In contrast to the secondary devices, where the flow is in both direction. Now, for the block diagram, the von Neumann computer, because you can be asked to draw the architecture model of the von Neumann as you can be asked to draw just the block diagram. And when it concerns the block diagram, you simply have the ALU and the control unit with the memory unit, this one, exchanging data. Then you have the input and the output unit, no need precisely the registers, the I/O controller, and the other components that are absent. Now, the processor can access the instruction and data in the main memory as required to execute the program using dedicated connection called buses. This is what we are referring to. This is what we are referring to. These are the different buses that we use. The same address and data bus are used in the process of transferring instructions and data between main memory and the processor. A third bus, that is the control bus, is used to synchronize and control operations. So, as you can see, these flow lines, we have the address, data, and the control bus, which together are used not only to transfer instruction and data between the memory and the processor, but also to make sure that these movements are synchronized with the use of the control bus. So that is how the flow is in a von Neumann architecture. Now, one important concept when dealing with von Neumann architecture is what is called the von Neumann bottleneck. Instructions and data in a von Neumann architecture are stored in the same memory unit and share a common communication pathway to the CPU. That is, this same line that we are having, it's the same line we use to transfer data and it's the same line we use to transfer information. This leads to a limited rate of data transfer, the throughput between the CPU and the memory. That is the number of transfer we have per unit time is limited due to the fact that we have a single pathway for both data and instruction. A situation known as the von Neumann bottleneck, that is memory CPU bottleneck, also known as the memory CPU bottleneck or the bus bottleneck. That is how it is being described. The von Neumann bottleneck arises from the fact that CPU speed and memory size have grown at a much more rapid rate than the throughput between them. That is, the speed and the memory size has increased more than the rate at which data is being transferred. Although memory may hold a lot of data that needs to be processed, and the CPU may be using only a fraction of its computational power, the limited data access speed prevents the computer from doing its work any faster. What does that mean? Although the size and the speed of the computer has increased, the rate at which data is being processed remains limited because of the only pathway that exists between the processor and the memory unit. And this situation is what we call the von Neumann bottleneck. And this makes the computer, it prevents the computer from doing its work faster. This problem is greatly reduced using the following techniques. We have the cache hierarchy, keeping frequently used data instruction close to the processor. That is, with the use of the cache, that is, this data instruction that we need to be processed frequently must be stored in a cache in such a way that the speed at which they are going to be accessed is going to be low. The multi-core processors spreading work across cores, but each core still faces the issue of bottleneck. The concept of multi-core processor is explained under parallelism. Harvard architecture, separating memory for instruction and data. So the Harvard architecture is an architecture type that suggests that the memory used for storing data should be different from the memory used for saving instruction, and hence we shall have two different pathways between these different memories and processor. And as such, the von Neumann bottleneck is either going to be eliminated or greatly reduced. Data flow architecture, eliminating the concept of sequential instruction execution and instead compute a process as soon as its input data is available. That is, as the von Neumann architecture functions on the stored program concept, in which one of the fundamental concepts is that instructions are executed sequentially. The data flow architecture suggests that instead of doing this execution sequentially, we must compute a process as soon as its data is available. So these are some of the different techniques we can use to greatly reduce the problem of the von Neumann bottleneck. In the next video, we are going to look at the Harvard architecture, which is one of the architecture that solves the problem of the von Neumann bottleneck. As the von Neumann architecture, we shall give the diagram, we shall explain, and we shall give the block diagram, and we shall go further to see the differences between this architecture and the von Neumann architecture. Thanks for watching this video. See you in the next lesson. Do not forget to like, to subscribe, and to share the video in order to increase our community. Thanks, and see you in the next video.